Hello, everyone. Welcome to our webinar today. Please confirm in the chat that you can hear us well, and let me know if you can see the slide of the presentation. Please use the chat to your right to confirm that you can hear me clearly and that you can see the slide deck. Okay, all good. Nice. Perfect. So nice of you to be joining us today. So I want to welcome you today to our webinar. We are running the webinar by Qualistry with cooperation with UPRI. My name is Jan. I will be your main moderator for today. And today's discussion explores the topic, how to utilize your temperature mapping data to improve compliance and efficiency. We have a slight change in the plan today as Jakob Konradsson will be stepping up instead of the original planned speaker, Arsalan Basir, due to business-related necessities. But don't worry, our new speaker is fully updated and he is highly experienced, and it will be a great session anyways. So in this webinar, you will learn from Jakob and Chris Maugun how to revolutionize your approach to thermal processing by harnessing the power of temperature mapping data. Be aware that the webinar will be up to 75 minutes. So this is the plan that we have on the table. And we will have a Q&A session at the end. And depending on how we run with the session, then we will decide if we can take a bit more time with the questions. So we'll see how it flows. Please be aware that if you stay until the end of the lecture, you will receive a free certificate of attendance sponsored by our event partner, UPRI. So make sure to stick with us at least until the end of the lecture. And we will send the certificate to you within several working days, up to 7 working days. So please be patient with it. And as you may know, at Qualistry, we aim to provide pharma professionals worldwide with freely accessible education and industry insight. And we managed to do it with the help of our incredible partners. And for this webinar, our partner is UPRI. And a big thanks for doing this webinar with us. And I would like to invite Adam, the co-founder at UPRI, to say a few words about the company and introduce our incredible speakers for today.
Thank you very much, Jan, and hi everybody. We are mega happy to see you once again, and with yet another very strong crew of speakers in here. Well, basically we're not in here, all of us. Jakob and I, we're sitting here in Copenhagen in Denmark, and Chris, you are live from, I think, United Kingdom, right? It's not Ireland, sorry, it's United Kingdom.
That's right, yeah, from the UK.
Where in?
In the northeast near Newcastle.
Right. Well, we are kind of on the same altitude, aren't we? Yeah, I think so at least. And hi to everybody out there. Thank you very much, Jan, for the presentation. And we are so thrilled to see so many people being part of this this webinar again, with a theme that is quite more specific than what we are typically used to. So I hope that that we're really gonna do some deep diving into to the specifics here. Utilizing your temperature mapping data to improve compliance and the efficiency of a temperature mapping is super relevant when you are an experienced validation engineer working with this field, I assume. And that's basically what we're gonna talk with Chris and Jakob about. So first of all, I just want to brief what's gonna be about today and why we are here basically. We started up 10 years ago, Jakob and I, when we met working with fields of kind of likewise the themes basically, and we realized that we could just develop so many mega cool products in this field. And when it all come down to like what the effect of them were, we realized that was kind of like, it always traced back to that audit that whatever software we made for validation or hardware-specific data loggers and sensors in monitoring applications, or this fantastic calibration lab we have created here in Copenhagen, it all came down to that we provide our customers with a significant easier audit, basically. It's just like with 3 clicks, you can create an audit report from our various different systems. And that's kind of why we in UPRI tell with pride that what we're working for is to create this like one-stop solution for temperature compliance. And that has led us to meet so many super interesting people, such as Chris, that is our speaker today, together with Jakob. And Chris has 16 years of experience, and today is working with validation and is hosting several validation workshops that I'm quite certain would be beneficial for many of you out there. Jakob, on the other hand, is my companion and partner in crime. We've been working together with this topic for so many years, and I was so proud back in the days when Jakob, he just like poked me on the shoulder and said, Adam, you kind of need me for this. And I'm quite certain that that was a very, very good decision because what Jakob has built is incredible. I have no other person that I've met ever that can just put himself into a standard in I don't know how fast time. He's an electronic engineer with space engineering as a specialty, so you could do whatever you kind of like, and that's kind of impressive.
Let's hope so.
So that's why Jakob is here, because you've really been deep diving into this for ages now. And I think we have collected a very interesting team in Chris and you to talk our way through this topic. So that's the theme.
Yeah.
And welcome. And to our agenda. Take it off, Jakob.
Yeah, so today we'll be talking about process improvements in terms of temperature validation and temperature compliance. And Chris and I, we've divided the topic down into 4 different pieces that we're going to talk about today. I'll take some of them, and Chris, you'll take some of them as well. I'll start out with the first topic of today. If I can get my screen up here. So the first topic of today is how to do process improvement based on the temperature mapping reports and the temperature compliance as a whole. And we'll kind of deep dive into some of the major topics in terms of how to utilize that for improving your processes. So some of these things that are really interesting to look at is, first of all, looking at the operational procedures. When getting a mapping report, we've been through this in previous webinars, and there are a lot of interesting articles to read from those and the previous webinars. But one thing that's really key in terms of using the results from your temperature validation is to actually take a step back and look at the operational procedures. So review those based on the findings from a temperature mapping or a thermal validation. One thing as an example is to look at door openings and closings, gates if it's a warehouse. There sometimes is a tendency to view the outputs of a mapping as sort of a binary conclusion, stating, well, it succeeded or it didn't succeed. I think in my view and many others, that's sort of wrong to see it that way, or at least not optimal. So one thing is to look for, well, if we take the example with the door opening, rather than saying, yes, it could succeed 15 seconds opening and then 2 hours of close as an example, rather than that, taking a look at what is my maximum door opening times. So taking the findings, and rather than looking at them as pass or fail, rather taking a step back and looking at your procedures and say, what can we optimize and how we use it operationally? And that goes for everything from smaller units, standalone units such as fridges and freezers, up to larger warehouses. So using those results to optimize the workflow, basically. Another key takeaway, I think, is one of the major pitfalls that we often see is that we validate either standalone units, warehouses, trucks, whatever it might be, in terms of a temperature validation, and the report is approved by QA and then put in the drawer and is never used for anything. So one of the key takeaways should definitely also be staff training. let the operational staff know what's in the report, what's the outcome of the report, and how should we use these results going forward. Because it doesn't matter updating your procedures if you don't train your staff on those procedures and what it actually means, what the contents of it is. That will surely have a large impact on the overall thermal compliance. That people know how they can open and close gates and doors, but also that they know that this equipment is well suited for temperature equalizing products, or it's not well suited for it. One of the findings some of our customers tend to have on the backside of a thermal validation is also power failure studies. So you might have a power failure study that shows that you have 6 hours to react in case of a power failure study before you have non-compliant temperatures. Well, if no one is trained in responding to those 6 hours and having those 6 hours to run on before backup generators need to be initiated, or an electrician needs to be contacted, or some other things, then it's no use. It all ties back into business continuity and disaster recovery as part of a larger GxP compliance setting, you could say. But staff training is really important in order to draw some of those positives out of a thermal study. So another thing is, and I know Chris, you're going to take over and talk much more about this, is basically to review the data. And I'd like to have just a few points in terms of how to review data. First of all, it's often dictated by different standards and guidelines to look at cold spots and hot spots. We much more prefer to call it cold and hot zones. Because in relatively a lot of the cases that we see, it's not a single sensor that's either the hot spot or the cold spot. It can be by single measurement, but it makes good sense to review the data in order to visualize in which areas we see higher temperatures or lower temperatures, and then again using that for optimizing your process. One of I think the success stories we've been through with our customers have been in terms of having customers that have products which are very sensitive to temperature variations and products that are less sensitive, often connected with thermal mass. Well, you might have some spots that are varying a lot of temperature, but if you have a large thermal mass of your product, it makes sense to store those there. And for the ones that are more sensitive, store those in more stable zones. So in that sense, using the outcome and the data from your mapping reports makes really good sense in terms of optimizing your process. I think that's one of the things we've often seen as a positive outcome. Another thing is tendencies when actually reviewing your data. If you see tendencies in the mapping reports that could kind of indicate that during the time of mapping there was not an issue, but you know that during your normal processes where it's winter and it's summer outside, could sort of have an impact on your daily processes. So where do you store products? Where do you unload them and offload them? Yes, as we see here, also changes in weather conditions and use. Are there any differences in terms of whether it was cloudy during that day? Could that have sort of an impact? So it often makes really good sense to look at the data and take that back to your daily operations. And then I'm going to give the word to you, Chris.
Let's see there. I think you're on now, Chris. Yeah. And now you're unmuted also.
Perfect. Can you see my screen okay at the moment? Hello?
Yes, it should be perfectly fine.
Okay, great. Hello, everybody, and thanks for joining us today. So I'm going to be talking, first of all, about predicting and preventing failures. So one of the things that I wanted to get across, particularly in this webinar, is it's not just a tick box performing temperature mapping. It's not just something that you have to do, and it's something that you put a tick in the box to say, yes, we've done the mapping, that's over. There's a lot that you can take from it. But in order to do that, in order to pull all of the information that you want, you need to start correctly. And that can really be benefited when you focus on risk assessment at very start before you've even procured some of the instruments that you're going to be mapping. If you do that correctly, then you can both predict failures and you can prevent them as well. So we're going to optimize that process. We're looking at what we're going to be working with, what the products are that we're going to be storing, what equipment we're going to use to store them in. If we can understand all of that information before we start thinking about temperature mapping, we can then look into it in greater detail. And by optimizing the process based on that information, we can gather data on worst case locations, on what is going to impact that particular product. So by focusing at that at the very front end, you can make sure that you're storing your product in the right environments with the right pieces of equipment. So risk assessment, performing that before we do anything else is going to make a big difference. So the process, and what we need to do is risk assess the process and the product. So if we start with the process first, so we want to know what's going to happen with that product. What temperature does it come into the unit? So for example, if we were bringing product in at minus 80 degrees, if it comes into the unit at minus 80 degrees, it's going to involve different testing to if we had to freeze that product down to minus 80 degrees. And that would have a different impact on the mapping that we would need to perform. If we need that unit to pull down, so pull down to minus 20, we would want to incorporate that into some of the testing. We also need to know about the product. So is it patient critical? What exactly are we storing within it? What volume are some of the items that we're going to be storing? Is it very low volume, sort of 1-2 mil? Or are we looking at things perhaps 500 milliliters or a litre? Or are we using boxes? And what is the volume? How much space do we need within the unit? If we can think about all of this information before we procure the unit, then we can purchase the right unit for that application. So we need to think about the quantity of the product and the volume it's going to be stored in. Now, we're talking today about how we can prevent failures and how we can use data to do that. But if we start from this perspective, we can start to understand more about the process itself. So this is taken from, this diagram on the screen now is taken from ASTM 2500. And essentially, this is about performing a system impact assessment. And if we can do this by looking at the knowledge of the product and the process, that's going to form a big part of the requirements that we need and the specification and the design for the temperature controlled instruments that we're going to be using. So we've got our regulatory requirements, which also feed into that. And we also have any company requirements that you might have. But the product knowledge and the process knowledge is critical to make sure that we can control the temperature within that unit correctly. So we'll take those requirements through to the specification and design phase, and then we can move into verification. So that's where we do a lot of our temperature mapping studies. So this is all of that information feeding through until we get to the verification stage. And once that's accepted and released, that piece of equipment can then go into continuous use. So that risk assessment is going to tell us what kind of tolerance ranges we need. So is it a 2 to 8 degree refrigerator? Is it an incubator that might have humidity or CO2 as well? It's also going to look at the frequency, the mapping frequency. So how often do we need to perform temperature mapping? If this is an instrument which isn't patient critical, then we might do it less frequently. If there's no issue with the product, again, we might do it less frequently. So we decide that frequency based on the criticality of the unit. So we use those system impact assessments at the start to understand what the unit's going to be used to store, how critical it is. And then we can identify risks and how to detect them. So I'm going to use the example of a very low volume of fluid. If you've got perhaps 1, 2, 3, 4, 5 mil of fluid in a vial, a bottle, or an ampule, that will go out of tolerance very quickly. So if you were to open the door on a refrigerator and that was at the very front, it's going to shoot out of tolerance almost immediately. So then we now need to see what is the impact to the product if we do that. So this is starting to formulate how critical that unit is and how critical it is for the products that we store within it. And that'll help us define whether we buy a fridge like the one you can see on the screen, or whether we say, actually, this is a really critical product. We're going to store it within a cold store that's less susceptible to fluctuations when that door's opened. So if we think about that at the very front end, how it's going to be used and what products it's stored within it, we can start to put that criteria in at an early stage. But then we can start looking at things like ongoing mapping, so the frequency of that, and periodic review as well. And it's really periodic review that's going to give us a lot of good data. So periodic review is going to help us understand what status that unit is in at the moment. So we start off with our risk assessment at the very front end, and that's going to give us the most common failure modes. So we'll assess things like, is there an issue with potential ice buildup in a freezer? Are we likely to see things like failures of door seals, fan failures, cooling or heating system failures, all of those kind of things? And then how can we prevent them? And that's what we're all here for today, really. It's how can we prevent these issues arising? So in the example of the ice buildup that you can see there, and like Jakob mentioned earlier on, if we can proceduralize with staff training and look at those SOPs and start saying, every time you open the door, look into that freezer. Is there an ice buildup? And then you can start to think, well, perhaps those staff need to be trained in seeing that, identifying it, and then resolving it. If you open that freezer every day, you tend not to see these things because it's slightly worse than it was yesterday. But if you train your staff how to do it, and if you place an ice scraper on the side of the unit, that's even better. You can open the door and remove that issue. But you can also add things like preventative maintenance, and they prevent it too. So by using the SOPs, preventative maintenance, that's helping us reduce that risk. And the temperature mapping is helping pick up a failure if it's present. And then we've got monitoring and alarm probes, which help us detect it if it is going out of tolerance. So we can use all of these factors to help minimize that risk and optimize the process. And if we do this correctly right at the front end, then we're reducing the likelihood of seeing any ice buildup, for example. We've empowered our operators to see it, identify it, and understand that it's a problem. We've also got preventative maintenance coming regularly to check these things. And if we set our alarm probes up correctly, we're going to detect it using our alarm system. We're going to get notifications to say there is an issue here. So we can do all of that, and we can also use periodic review to check on it. So the alarm system will generate deviations if there's a problem. We'll also have issues highlighted through the deviation system if there's been issues with product. All of these things can be assessed on a routine basis using periodic review. So that risk assessment in the start is going to help us sort of procure the right unit for our application. So in the example I gave, we might end up buying a cold store rather than using a fridge or a freezer. And we want to make sure that we've got correct sensor placement within there. So we're looking at where we're going to be storing product. So it really should be a scientific basis. Are we going to be storing product in the full usable space of the unit? Or are we not going to store product on the base of the unit? If we're not, we don't need to map it. Where are we going to place our sensors? Are we placing them right up to the usable height on the top shelf? So you can see the sensors in this picture, they're positioned so that they're towards the top of the unit to accommodate for the shelf. We want to detect failures. So when we identify our hottest and coldest locations, we're using that information because that information is hopefully going to help detect any out of tolerance results that we're using. So those locations identified during our temperature mapping are going to provide the worst case locations that we can use for ongoing monitoring. So they can identify those worst case locations that we need. So this is kind of a map of how we would normally look at the lifespan of a temperature controlled unit. We've got the risk assessment that we're starting with, moving on to our initial temperature mapping, where we look at sort of installation qualification, operational qualification of that piece of equipment. We perform our temperature distribution studies. We might do load penetration studies where we're looking at the temperature of the product itself. And then we'll do things like door open tests, power failure tests, and we might do pull down tests as well if we're performing, if we're freezing product down. Once we've done that initial temperature mapping, we can then start looking at a periodic review. And for that, we'll pull all of the data. We'll try and look at the alarm probe. We'll look at the different feeds that are coming through, any deviations that are associated with that equipment. We use all of that to analyze the data. What's the minimum and maximum temperature? How long is it going out of tolerance when we do door open tests? But also, what's happening with that data? Is it trending the same as it was a year ago? Is it starting to control slightly higher in temperature or slightly lower? So that periodic review is using that temperature mapping data that we had originally. We take a look at that. So we've done our initial qualification. We're a year later. Let's pull that data out, take a look at it and see, are we still operating in the same way that we were a year ago, 2 years ago, 3 years ago? And we can use that information combined with the temperature mapping to ensure that we've got ongoing compliance. So temperature mapping really is like a snapshot. We do our temperature mapping, and it's absolutely necessary that we do that, but it doesn't ensure that we've got good control throughout the year. The periodic review does that, because we use that to check the data, make sure we're still in tolerance, make sure we're not having any issues with things like defrost cycles, that kind of thing. So we cycle between the two. We do temperature mapping and periodic review together, so we can pick up any failures as we move forward. And if we had a failure during the periodic review, that might instigate another temperature map to make sure everything's okay. And then if we do have any major changes, if we're going to move that unit, if we're going to go somewhere else, it's at that point where we would say, you know, let's remap. Let's take another look at this. There's something gone wrong. We've moved the unit. We've potentially changed the way it operates. We've changed shelves. We've got a different product in there. We go back to square one and we start again with that risk assessment. So periodic review takes a look at things like the calibration history, equipment logs, deviation investigations, maintenance repair history, operational procedures, the ambient temperature profile in the room. We'll look at the monitoring system as well, the temperature mapping studies, and not just the last one, but the ones before, and then existing qualification documents and equipment procedures as well. So we're looking at everything, combining it together. We're trying to understand exactly how that system's operating and how we can go forward with it. So periodic review, it's a combination of mapping and periodic review will help us detect and predict things like control probe drifts. It'll also help identify things like heating and cooling failures, if we've got issues with fans, defrost cycles, all of that. So we're looking at using that risk assessment to help identify potential failures. And then we're using things like the alarm probe selection, the frequency of mapping and periodic review, just to make sure that if we do start to see failures, we want to pick that up as early as possible. So we're doing everything that we can to detect it. So we're using that initial qualification and the ongoing requalifications to ensure that it's all okay. So this is a bit of an example. We might take a look at some data in this refrigerator. So we've got some example data here where we've got a minimum temperature of 3.5 degrees and a maximum of 6.1. We've got hysteresis in the machine and it's controlling pretty effectively. We've got good control in the center of the temperature band, right where we want to see it. So that's good. We might come back next year and see that that control's changed. We've broadened that temperature band. We're now very close to failure at the upper end. We've got a minimum temperature of 2.2 and a maximum temperature of 7.9 degrees. We want to pick up issues like this as early as possible so we can start to rectify them. So that's where we utilize things like ongoing monitoring and mapping together to see if we're starting to trend out. We don't want to stop using this unit because it's failed. We want to predict that failure and avoid that issue. So this is the ideal. We've got a temperature control here, and ideally we're looking to have a buffer at the top and at the bottom of that temperature band to ensure that we maintain control. We want to make sure that we control within that temperature band so we have good control and we don't see us going close to failure. We want to stay with as much within the center of that temperature band as much as we possibly can. Okay, so I'm going to pass over to Jakob on energy efficiency.
Thank you very much.
Thanks, Chris.
So we're going to talk slightly about energy efficiency, and also that often relates to some of the efficiency in terms of maintaining homogeneous temperatures, because a large part of energy efficiency is, of course, insulation. I think, first of all, it's quite important for me to mention that we, at least from our standpoint, start to see that energy efficiency and also the reduction of CO2 on the backside of that is something that's becoming more and more important for more of our customers. I think for a lot of years, the largest importance was to ensure that the product safety is max priority. It still is, of course, and luckily it still is, but we also start to see energy efficiency being part of the company's goals in order to have a positive impact on global warming. I'm going to go through some of the steps that will both benefit energy efficiency whilst maintaining compliance. So first of all, I think it's very important to have sort of a data-driven insight in terms of looking at providing any guidelines and any pointers on how to optimize the energy efficiency. First of all, one of the common things to look at is to analyze the mapping data in terms of trends and fluctuations. A large cause of fluctuations when you're dealing with fridges and freezers, and in some regards also warehouses, has to do with equipment that has either lost its insulating properties or is about to do so. So when you, Chris, talked about going back and reviewing that data, not only at the point in time of your mapping, but also on the trending side, that really gives a large insight into looking at whether it could be beneficial to look at improving your energy efficiency. So that's the one thing when we're talking about insulation. The other part is also looking at how to set up your HVAC systems. I think this is often more easy to do when talking about warehouses, where you can have larger HVAC systems that can be tuned in. But we've seen plenty of our customers who had large benefits in terms of being able to tune the HVAC system using multiple coolers, also to reduce ice buildup. Another part of this is also insulation. And this really takes a step back in terms of how warehouses are designed. I think one of the most prevalent cases we see out there is especially when you have warehouses that were not built with the intention of having those as temperature controlled. And we see that the insulation that you see on large surfaces, but especially also roofs, tends to be insufficient, not in terms of maintaining temperature compliance per se, but in terms of being able to not use enormous amounts of energy. And I think this is also a point where energy efficiency and compliance goes hand in hand, because we do see examples of power failure tests that are simply unacceptable due to the fact that the temperature will simply rise or fall way too quickly outside those acceptable limits, simply because the insulation is not sufficient. And one thing is common insulation. I think that's often the thing that is referred to. Another really large cause of both the use of energy, but also the causes of deviations are sealing issues regarding either fridges and freezers, where your rubber sealing tends to be either frosted up or damaged in any other way, simply due to the use of time or over the course of time, or based on actual damages. Another big thing we see about sealants is for doors and gates in warehouses, where they are simply not designed to be in a temperature controlled environment for that temperature range. And that can cause both energy insufficiencies and also deviations. So that's a very large part to keep in mind. And we have another part here, sorry. Another part about energy efficiency has to do with loading capacity. So one of the things to keep in mind, and Chris, you mentioned it as well in terms of usable volume, is the amount of loading that's ongoing. Both that and temperature equalization or frosting of goods. So basically, is the system designed to freeze in products, as an example? It could be phase change materials or other products that need to be frozen in, or is the amount of loading simply not suitable for the volume that you're trying to utilize? That sometimes, often these HVAC systems and compressors in fridges and freezers are designed to a specific amount of cooling capacity. And if by either loading too much, or even in some cases too little, or using them in unintended ways, they simply go out in the area where they become very inefficient. That also, in terms, again, can lead to temperature variation simply because you do not use the time properly to freeze in products, or the temperature stability and homogeneity can be heavily affected. And another huge part of this is storage and placement of goods. So first of all, for standalone units, having free air around a standalone unit, something that we often see becoming an issue, because you need ventilating airs for the hot side of standalone units. And also whether those standalone units are placed in a temperature controlled surrounding. One odd thing we often see there with our customers is that a lot of energy is being used to keep it at a very temperature controlled surrounding, but at elevated temperatures. So having using energy and heat to warm up those surrounding areas, because you want to stay exactly in the middle point between your boundaries, does simply not make sense. If you're storing standalone units in there, they can be perfectly fine. But if you choose to store them at lower temperatures, the energy efficiency of those standalone units will be highly elevated. And of course, another thing we see where the risk assessment really comes into play is in terms of the temperature setting. There is a general tendency to want to be placed just in the middle of the temperature zone. So if you have a 2 to 8 degrees storage, you want to place it at exactly 5 degrees, which makes sense in terms of risk. But one of the things that we tend to see have a benefit on energy consumption is looking at tendencies, being more diligent in terms of reviewing the data that's from the ongoing monitoring, and choosing to see whether you could move the temperature set point slightly upwards in the case of a fridge. This would mean, of course, that we're closer to a deviation, but still, if there's enough space in terms of homogeneity and stability, just placing the temperature set point slightly higher has a really large impact on the energy efficiency. And the last part I want to mention has to do with zone-dependent settings. It's something that we see in warehouses, where often large HVAC systems have the possibility to be zone dependent, so that you have areas of the facility that are not close to doors and gates, as an example, which can be less delicate controlled, which would often mean that the cooling systems would have to run for shorter or longer periods of time, but with further spaced. That would give a higher stability, which is not as good, or a lower stability in how you see it, but often it has very little impact on product stability. So that was it for me. I'm going to hand it over to you, Chris. Thank you very much.
Thanks, Jakob. That was really good. Yes, so we're looking at ensuring control and minimizing failures now. So let me just take a look. So there's a few failures that we can see on an ongoing basis with our units, and we can optimize and prevent those by doing things like control optimization. So optimizing the sensors that are controlling the systems. We can look at things like ice buildup and defrost cycles. They can be a common problem that people start to see. So we'll need to look at those. And also the airflow distribution within the units as well. These are kind of the three main areas that we tend to see that we get failures on quite a lot. So let's just take a look at a few examples now on those failures and see where we get to. So the first thing here is control probe optimization. So we would normally optimize a probe during the OQ phase of a new unit. So for example, if we were to map a new incubator, we've got a 22.5 degree set point on this incubator, but from the data here, it's controlling quite high. up at the upper limits of that temperature band. It's getting close to 25 degrees. We've got really good control in this example. So we're very much in control around 24 degrees, but really we prefer to optimize that control a little bit lower, towards the center of the temperature band, so 22.5 degrees. The reason why we want to do that is we want to have the maximum difference really between the limits of the tolerance ranges and the control set point. So the ideal for this unit would be that it was hovering around 22.5 degrees. Sorry, the slide doesn't quite do it, but this section here is controlling at 24 degrees. We want to see that lower to the minimum of range right in the center here to around 22.5 degrees. We would do that during the OQ phase. So we're looking at the calibration of the probe and the control of that sensor. So we might adjust the calibration to ensure that the whole of the unit controls correctly within that center of the range. But also, if we start to see drift within that unit, if we start to see it slowly going out of tolerance, we then want to take a look at that too. So this is where the periodic review that I talked about earlier on comes in, analyzing those temperature mapping data. Yes, this has passed. So you've ticked your box. You've said we've passed, but it's not controlling right in the center of the temperature band. It might have drifted since the last qualification. It might have slightly increased. So we need to think, what happened last year? What happened the year before? Are we slowly moving out of tolerance? And if we are, can we bring the calibration of that control sensor into tolerance? A lot of people don't calibrate the controlling sensor. You rely on the data from the monitoring system. So they're using that monitoring system to have control. So we've got a few comments about MKT. I think we'll deal with that in the questions. MKT is usually only used for warehouses. So that's why I'm not talking about it in these slides. MKT is normally operated for units between around 15 to 25 degrees and only accepts tolerances up to about 30 degrees. Personally, I don't normally recommend the use of MKT. If you've got an out of tolerance result, it's far better to sit down and take a look at that data. What is going on? What is the cause of that out of tolerance result? So if you use MKT, you're looking at a way of accepting that data because the MKT will be within the tolerance range, but you'll have a high temperature out of that tolerance range. So you need to investigate it. And I think just by saying it's within the MKT tolerance, it isn't really a robust enough investigation. What's the cause of the out of tolerance result? For things like warehouses, that could be like an external temperature that's coming in. So it could be due to a skylight. It could be due to doors opening and closing. It might be a particularly hot day outside. But the investigation is important to trying to understand it. But I'm sure we'll deal with some MKT questions at the end. So we need to optimize that sensor drift. So if it's starting to go out of tolerance, let's deal with that situation and try and resolve that as we can. Another issue that we see that's really common is ice buildup in freezers. It creates all sorts of issues. Ice acts as an insulator, but it also impacts the airflow within in the chamber. It's really easy for it to build up over time. And it can be quite difficult for operators to notice. If they're accessing that every day, that slow buildup of ice is going to cause a few problems. So we'll want to try and optimize that. If we've got, again, I'm not sure my graphs are working here. No, they aren't. So we've got some data here on the left-hand side. We've got control there within our unit between -70 and -90. We had another graph there you can't quite see where we had an out of tolerance result. So we had temperatures going up to, I think about -65 degrees. Now that unit hadn't failed, that unit hadn't been de-iced. It required a de-icing to bring it back into tolerance. The ice was impacting the temperature within the unit, and we had out of tolerance results. So the acceptance criteria for that ultra low freezer was -70 to -90 degrees, and we were getting up to -65 because of this ice buildup. So the way we can get around that is by using things like SOPs, so that the operators know when they go in there and they see this ice that they need to scrape it down. I always find if you've got an ultra low freezer that's prone to ice buildup, if you put a scraper on the side of the unit, people will use it. If they have to go looking for one, it's an extra complication in an already busy day that's difficult to achieve. So optimize the process, place it on the side of the unit, and you can prevent those out of tolerance results from happening. Because in a worst case, if you don't pick that up until the next temperature map, what's happened within that unit for the last period of time between that temperature mapping and the previous one. So operator training, staff training, really useful for de-icing. Preventative maintenance, if we've got regular preventative maintenance, taking a look at the chamber and then de-icing where necessary, and popping that ice scraper on the side can be really helpful. So we've got a couple of questions. We've started periodic review of equipment instead of a yearly qualification. We monitor the hot and cold spots. We check the data on a monthly basis. Is requalification with a mapping still needed? Is mapping still needed periodically if the review showed no deviation or changes? Roger, I would say absolutely yes. So the thing with the periodic review and the temperature mapping is we cycle them. So the periodic review is great. It's going to help us pick up on issues, but it's not going to tell us the whole story. So if you think, for example, if you get a fan failure in an incubator, that could change where the hottest and coldest locations are within that unit. So we might have our alarm probes at the top of the unit, but we might start to see hotspots at the bottom. So it's belt and braces, really. We're using the temperature mapping data is critical. It's really useful. But the addition of the periodic review can help us push out that temperature mapping frequency. So rather than map every year, we can push it out and start to map every 2 or 3 years or something like that. I think we'll deal with some of these questions at the end, I'm guessing, because I'm sure Jakob would like to join in on them. But question regarding the utilization of temperature mapping data, could you please provide some guidelines on setting a temperature alarm limits and delay times for permanent monitoring sensors? Specifically, how would you differentiate between limits for single coverage monitoring based on either the hot or cold spot versus dual coverage based on hot and cold spot? Well, it really comes down to criticality. How critical are the products that you're storing within it? And that's why that risk assessment at the front end is so important. Do you need to have 2 probes? Is it really critical? If it is, put 2 monitoring probes in there. It's going to give you a lot more information. So I would say that it really depends on what you're going to be storing within the unit. But as far as alarm systems go, the regulations on that are very different. We need to think about how are we buffering that probe? So is that alarm probe within glycol or a metal buffer? If it is, we don't want any alarm delays at all. If it's not, we need to think about what are the frequencies of that alarm? How often is it reading? Is it every minute, every 5 minutes? So we need to understand what the alarm delays are. So if we have a buffering on that probe and we had a time delay, it would take a long time before we would get an alarm saying that unit's out of tolerance. So really, there's no hard and fast answers on that. We need to look at this product that's being stored within there and the criticality of it. And if it's very low volume and very critical product, you want that alarm to go off as soon as possible. So we want to open that door and that alarm to shoot out. Ultimately, door openings causing alarms can be very frustrating in a lab environment where you've got products and units that have been opened and closed all day. So it's about balance. It's about risk to the product. And if it is a big risk product, it's about storing it potentially in a different unit that's going to give you better control. So I'll just carry on with the presentation. We'll take a look at some of the other comments. Hi there, Nathan. Recommendation on MKT. Yeah, I don't really use MKT at all. I've seen it used as a justification, but I'm not convinced it's the best method. I think you really need to understand where a failure has come from, and that investigation, that deviation triggered by the protocol failure, it is a good place to start. Okay, so that's ice buildup. Defrost cycles. This is a common problem, and I'm sure we've got a few people here that have seen them before. Defrost cycles, if you've got a machine that has a defrost cycle, on the plus side, you get less ice buildup. You're not going to see that ice buildup as often. You're not going to have to de-ice as frequently. You can reduce the preventative maintenance. But it's very common to see failures during your mapping process where you get out of tolerance results. During the defrost cycle, the temperature raises within the unit. And you start seeing temperatures like we can see in this graph. We're shooting up to sort of almost minus 10 degrees there in a minus 20, 25 degree unit. Now, there's a few things that we can do. Now, you can see in this graph what's happened here is the operating temperature has been lowered. So we're trying to control towards the bottom of the range, towards minus 25 degrees, to accommodate this huge defrost cycle. It hasn't accommodated the defrost cycle, so we're seeing out of tolerance results. Now, those out of tolerance results are because of the defrost cycle. Is it a problem? And for that, we need to understand the process. We need to understand the products. If it is a problem to your process and products, if it doesn't meet your site criteria, then we need to look into that and do something about it. And probably the best method is to reduce those defrost cycles. Sorry, my slides have just disappeared. Yeah, so we need to reduce the frequency of those issues. So we can remove that defrost cycle altogether and get better control. But it is always going to be a trade-off between ice buildup and those out of tolerance results on the defrost cycle. Some units can control better within the units, some are worse. It really depends on the manufacturer. So this is an example of better control that we would really want to see, but that might be at the expense of the defrost cycle. And if we did get an ice buildup, we would see that temperature rise within the mapping period. We would see that sort of increase if we saw an ice buildup in that unit. Identify the usable space. So this is something that's really important here. What do we do if we see a failure here? Sorry, I'm just trying to check these slides. So if we, first we need to understand what the usable space is within this unit. So is it the full height of that unit? It goes from the bottom storage. So we've got a couple of drawers in this unit at the bottom. If we're storing product within there, we need to map it. If we're going to be mapping at the top of that unit, we need to go right to the very top of those bottles. We need to cover that entire usable space in the top corners of the extremities and then across the space within the unit. If we see a failure at the top of that unit, we can remove that shelf from use. We can take the shelf out, we can remap it, and then say no product storage above that space. So it gives us the option to continue to use that equipment, but not that top shelf. But airflow distribution is one of the most important things within the unit. And this is something that's really difficult to pick up as a failure. So if we've got airflow distribution within that unit, it can easily be impacted by the loading of that unit. So if we've got somebody who is placing items within that load, it's good to try and proceduralize that and understand that the placement of those items can impact the qualification. And so we want to have good airflow, like you can see in this incubator. The items are stored evenly. We've got the fan working to distribute that air. That's helping with our temperature distribution across the chamber. So we're getting good temperature distribution within that unit, and then everything is working well. But what's the impact if we add boxes? And you can't see it on this diagram again, but if we placed boxes within that unit, kind of clip lock boxes, we would could easily effectively fill a full shelf with a solid layer of boxes containing air. And that's going to massively impact that air distribution within that unit. So what I always recommend, if you can, is that you avoid using kind of boxes that are sealed, and you use sort of cages or racks similar to this, where you get that good airflow. So the air goes through those rackings rather than being blocked and having to work around that unit. We're going through, so we get that good temperature distribution across the unit. So if you can, use this. We do see quite a few failures where we come and map units while they're in use. If they've got big boxes and a huge amount of load within that unit, it can impact that air removal and cause a big problem. Okay, so I think that brings us to the end. So we'll maybe go through some of the questions in a moment.
Yeah, and about that, thank you very much, Chris. That was super interesting, and thank you also for just diving into a couple of questions while you were at it. And out there, just keep coming up with the questions. They are so good. And thanks to you, Chris, for for starting up that part. And just before we start the QA, I just want to tell you shortly what we do and also maybe what Chris do. Because with UPRI, we basically uncomplicate your temperature mappings. And we kind of call it like a little less mayhem and more compliance confidence, basically. And the way we do it basically is that we make you avoid these costly delays that are typically, you are the bottleneck when performing mappings, because somebody is waiting to get that equipment into production, basically, or into place. And that's really what a nice solution helps you with. Particularly with us, it's all digital. It's all part of a big system that you can always get back to. Now, we talked a bit about trending, and it's something that we will also be working with in the questionnaire Q&A session. But that's really a big thing, that you can always go back to whatever was done, even in a digital setting. That makes it a lot more fluent, basically. There are no calibration blocks because we run a state-of-the-art calibration laboratory here at UPRI. Compliance certainty is a big word, but it's really what this is all about. It's about giving you an experience that just makes you go through to that audit and make you go through to a nice experience. And in the end, you can always call a friend. The way it works is that we can either give you a mapping kit and you can do it yourself, or you can get help from Jakob and his team from either a full on-site solution or a remote installation that we basically help you remotely and you can do it yourself again. In reality, it's about a software system and some mapping equipment. And this allows you to easily access some standard protocols and reuse them over and over. Imagine having like hundreds of cooling units that you need to map, and then just having a system where you can always just use these standard protocols and reuse them. There are some super smart analytical features for mapping that will speed up the process and enable you very fast to get these insights even before you end the mapping, then restart it because you know what the problem is already, because you have live data available. And then the last big thing here is get help from a friend. And that's really the reason why Chris and Jakob is here, because you can all hear the experience just floating out of these guys. And that's what they can offer you. In Chris's example here, I'm sure you can get access to some very, very relevant workshops. And if I'm not totally unsure, I think you can also share a link in the chat, right, Chris, to your workshops, I assume.
I can, yeah, I'll do that now. So those workshops, we run them once a month. They're like free 1-hour sessions. We've got one next week, actually, on Thursday. And we look at particular issues. So I work a lot with autoclaves, with quite a lot of sterilization stuff there. But we also work with a lot of temperature mapping as well. So there's quite a lot of content already available. I'll put a link on the chat now, so you can take a look at that if you'd like to. I think there's about 30 of them that we've done so far. Oh, sorry.
Nice one, Chris. And we'll do the same. Check out our catalog, look into our services, and then we are moving into the next step of the presentation, which is the Q&A. So thank you, Jakob and Chris, and thank you out there for all your very interesting questions. Just to start out, I'm gonna open my small blue book here. So we talked a bit about risk assessments, Chris, also with you, Jakob, but it's the theme we keep coming back to is risk assessments. And I have been wondering that when you have this, like you pitched, Chris, in the beginning here, that I'm just gonna put up you, there you go. You pitched that, it's a process and you start the structured way going through it all. And then you start with the risk assessment, but do you also come back to it? Because, I realize when you're out at the site and you've done all your protocols, you've done all the standardized work and your risk assessments before, but when you're out there seeing that this door was actually not the greatest invention in the world, or whatever, physical appearance of the place, do you then alter your risk assessments on site also and go back to that step, or how does that work? Chris, you're first.
I think the risk assessment is something that's often not done very well and not done sort of comprehensively before procurement. And I think that's the kind of the point I was hopefully trying to get across, that if you do this correctly at the very front end, if you start looking at that risk assessment before you purchase the equipment, you can then procure the right equipment for your application. And I think this is something that's kind of overlooked a lot. It's that we need to store within 2 to 8, so let's just buy a crate. It's a little bit more complicated than that. We need really good control for some products. For other products, the control's maybe not so critical. It really depends on the criticality. So we don't really want to go and buy the most expensive piece of equipment and always use that. And again, we don't want to buy the cheapest for really critical products. We want to be looking at exactly what we need. And where there is a big risk, we need to put other measures in place to prevent those risks. And if this is done right, this risk assessment's done right, from the very start, you can say, you know what, this looks like it might be a risk in the future. So how are we going to detect that if it does happen? So like a door seal on a unit can easily fail, and they do, we know they do. So it is a risk. You might, for example, if it was really critical, say, you know what, we're going to change that door seal every year. I mean, that's an extreme example, but you get my point. We can look at those issues and we can say, let's resolve that. Let's put a preventative measure in place to make sure that we can move forward.
And I think also, thank you very much, Chris. I think also to follow up on your answer there, I think I would often also love to see our customers and the companies out there utilizing risk management also in broader terms, in sort of going back to original question, Adam, going back to see not only do we have any sort of equipment risks that are related to that specific unit and those specific products stored, but also looking at have our process changed. I think some of the cases we have recently are also a lot of cases where the operational use of a system that mostly warehouses have changed, that either the amount of loading and unloading or the amount of people entering and leaving and forklifts and so forth have changed. And therefore, risk management should go in and revise those risks that have been initially estimated or made out in the beginning. So I think going back to your question, Adam, I think it's really important to go back and revise them and see them as a living document. But of course, without a strong basis, as you mentioned, Chris, it's not really a strong house you're going to build on that.
You keep coming, it's also, you said it all, Chris, here, that it's not something you see your customers do too much. But I know, Jakob, you're constantly talking about risk assessment, and I assume it's because there's a lot of benefits in it. Like this is also a topic where we just load people with all these mega nice processes. They're all super time consuming, and to some extent they are quite costly also. But isn't risk assessment, the answer to many of those problems, that you can actually, limit or make smart work instead of just making the work that is defined in the protocol?
Yeah, I'll pick that one up. I think that if you use risk assessment correctly, what you're doing is you're reducing the workload. So and maybe changing it a little. So having a downtime to perform mapping and other things, you can reduce the frequency of that. You can reduce the volume of work that you need to do, but you're replacing it with a greater level of control. So it has huge advantages, but it's often overlooked. People seem to think, this is a lot harder to do this. It's not, it's easier. You can download reports quite easily off digital systems these days. You have all of the data to hand. And actually what we want to do is prevent any issues for the patient, really. We really need to do everything that we can to minimize those issues, to minimize deviations, to save costs. And we can do that by reducing the temperature mapping, but increasing sort of preventative maintenance, maybe the alarm systems, maybe using 2 probes rather than 1, by checking routine data, looking at alarm logs. All of that can help us, and it is overlooked. And I think it's a real benefit to people. Whether it's less work or more work, I think the jury's out on that. It's somewhere in between.
And I think also maybe to exemplify that, at least in some of the scenarios we see, is that often the cost of constant temperature monitoring is measured sort of based on what is the lowest amount of sensors that can be used to store something like a warehouse, but not correlating that with how much is saved on being able to postpone per se a requalification or remapping. That's often not taken into account, because I at least see that the tendencies are going towards sort of what we call ongoing qualification, in which we utilize more sensors and more data analysis of the sensors, and using those on both the extra cost to have more ongoing monitoring and also the extra amount of desk hours. But that comes back tenfold in terms of being able to postpone a remapping, which can be quite a costly procedure. Of course, reduced by utilizing risk assessment. But basically, I also think that we're sort of at the edge of being able to utilize sensor data in a much more intelligent way that will help organizations have more qualitative data on whether a remapping is needed. I think that the rise of statistical tools and also the rise of smart sensor networks is about to push or give some hardcore data on when can we postpone that mapping. I think when we started out 10 years ago, the suggested requalification or remapping period was something like 2 to 3, 4 years, and now we're seeing sort of average frequencies going up in 5, 6 years. I don't know if you agree with me on that, Chris, but it seems that the data,
I sort of see 3, 5 years quite common now. Some people still just do annually.
Yeah.
I think again, it depends on the criticality. If it's really critical, why not do annually? But you know, there is a point at which you really need to do mapping, and it's not an endless list.
Yeah.
The worry I always have is a new unit performs very well when it's new, but by its 10th year in life, that's maybe where you want to start mapping a little bit more or have more control, because that's where you're going to start to get parts that are going to fail, like fans and etc. You know, so it's worth considering that. I think.
Yeah.
How many periodic reviews and requalifications? How often is that? You know, especially the requalifications. That there are so much equipment out there. How often is that actually followed? Is that a tricky question?
Yeah, I think I would go back and draw on, I think, my background in sort of calibrations as well, because one of the questions we also get is often, how often do I need to calibrate? And basically it has to do with the stability of, when you're talking about calibration, it has to do with the stability and drift of your equipment. So basically, if you have a good understanding of how much your tendencies tend to move. So back to the very good slide from you, Chris, in terms of how are your hot spots and cold spots moving, what's the sort of the homogeneity. I think that often when you have a good baseline of being able to not predict, but at least have some sort of qualitative answer in terms of how much are we changing over time, that can be used to determine the intervals of these regular reviews. We often suggest customers to have a very diligent and very shortly spaced reviews in the beginning, because then you'll start to have an understanding of how much does this drift. I mean, these hardcore numbers on how much are homogeneities and stabilities, how much do they drift over time? And if you're starting to see sort of a constant drift after some time, that will give you much better input in terms of determining the period in between reviews. I don't know if you'd agree, Chris, on that.
Yeah, I think there's a couple of things there with drift. The probes that you use are usually things like PT100s. They have very low drift in control. So it's unlikely that you're going to see the sort of extremity that I showed earlier, where we've got that sort of 2-degree difference over time. But you do get drift, and it does cause an issue, and that is the controlling sensor. I think that the more monitoring that we've got in there as well, that helps. You know, if we've got 2 probes in the hottest and coldest, one in the hottest, one in the coldest, we're going to pick failures at both ends, and that's definitely going to help over one probe. And your strategy for things like alarms, how quickly are they going to go off? All of that, I think, sort of needs to be looked at with the criticality of the unit, and together you kind of make an assessment on those frequencies. So obviously more critical units you're going to want to map more frequently and run the periodic review more often. Less critical units, sort of reagents, things like that, you can push that out a bit. So I think with what you gain more of the critical processes, and you maybe lose slightly a little bit of control of the processes which aren't critical. You change the way you monitor them. So you're using these periodic reviews. So it is, we're starting to see it a lot more. People are moving to this kind of way of doing it a lot more now. Definitely getting more popular.
And I think also maybe to add to that, I saw some of the questions through looking at, I think one important thing to mention is also that in my perspective, there's a very large difference from just looking at the amount of alarms received during a period. And that's something different from looking at tendencies. I think that's very important for me to underline that just looking at the amount of alarms that you see during a period is not really indicate a good indication of whether you have a bad or good tendency in terms of your stability. Because if you're already reaching the point where you start receiving alarms on a more frequent basis, you're basically already outside the scope of or outside sort of the tolerable limits of in terms of having a good tendency of those storage conditions. I think it does take some insights into looking at data when reviewing these tendencies. It's not as easy as it might seem, because you cannot. We've seen plenty of customers, at least, who have only looked at the amount of alarms, and then it's basically a bit too late, in my view, at least.
Right. We have a question from Nils that I think is interesting to just talk about briefly. Nils Elmegård Dikov, he mentions that, when you have a mapping of a unit, you have it without and with load. The material inside, depending on what it is, obviously, but it could have a very big insulating effect of it. And I just want to add another part of this. In a real life scenario, you also have something in between. You have the cases where it's completely full and 100% load, and you have like 50% load, I assume. How do you, what are the values that you that then confirm the true cold and hotspots, just to recoup on that initial question?
I think, if you allow me, Chris, I think one of the major misconceptions, or one of the major pitfalls we often see is that people will tend to look at only peak temperatures. So what was the single measurement during the measurement cycle that was the hottest, and the single measurement point that was the lowest? I think that's kind of, I think also referring back to what you said, Chris, about having to look at data rather than just using MKT. You have to understand sort of the data. That's one part, and the other part is often that calibration uncertainty or maximum permissible error, also in that connection, is often not taken into account. And lastly, also looking at sort of hot and cold zones, because it's often that when you take the calibration uncertainty into account, there are several loggers in which their average or peak temperatures, however you look at it, might be in sort of in the hot area or in the cold area. And I think it has to be sort of more holistic view at looking at all your data loggers, rather than just picking out that single point in time.
On the min and max, I just read Nils' comment there, and I think he's absolutely right. You do get this packaging, this buffering. You get very large volumes, very small volumes, and there is this sort of element of, if you have a sensor in free space and it goes out of tolerance, but you've got product in sort of a cardboard box that's then in a bottle with 1 liter of solution, the stability inside that bottle it's not going to go out of tolerance like a probe in free space. So there is an element there where you can say, well, we can buffer some of this data, or we can accept certain out of tolerance results based on the fact that we're storing large amounts of product. I think the use of MKT, which I think is part of his question, is it? Maybe not. Sorry, I thought I read that. No, I don't think it is. So yeah, I mean, we see this all the time. I think there is a reason there to justify maybe using a buffered sensor, or to accept out of tolerance results based on the product that's stored within it. you do get this sort of buffering impact. You do get this kind of high and low temperature effect. So yeah.
Thank you, Chris. And first of all, now we are actually at the end of the webinar, but I really feel we are not completely done yet. So, you know, all of you who don't want to miss the last part, you're welcome to just join for a couple of minutes more when we close it down. But the rest of you who has other things to attend, well, thank you very much for attending. And it's been wonderful to host this webinar again. And with you, Chris, it's really, really cool. It's been so interesting to hear your point on this. And I'm quite sure we will recatch something on this part later on. But we're not done yet because I just have a couple of more questions. And Niels also had a comeback. So let's talk about that later. Riona, she has an interesting point, I think. That is, you know, when you have done these mappings and you figure out that you have several hot spots and several cold spots, I think we can allow ourselves to talk a bit about these zones. Like what does it? How do you then determine the real spots slash zones when there are more? How do you go about analyzing your way into like determine in the end? The reason for her question is the placement of the operational, the temperature monitoring when it's running. How do you determine that?
You want to go, Chris?
Yeah, sure. Okay, well, listen, if you've got some temperature sensors that are out of tolerance, but you might even get exactly the same temperature, you know? You might have 2 or 3 probes that are the same. Really, we're looking at a scientific rationale for the placement of an alarm monitoring probe. So if you've got a high temperature, let's say it's 7.9 degrees in 3 separate locations, really, just place your sensor in the most easiest to place the sensor. It's not, if it's in the center of the chamber, let's say we've placed a probe right in the center of the chamber, we can't, if we put our probe there, and I'm sure you could, but you would impact the loading of that unit. So these are practically used. We're placing things on them on a daily basis. We're looking for the best method to pick up a failure. If we've got the same sort of area that's out of tolerance, and one of them is better to place a probe, that's the one we're going to go for. And this is in the ISPE guidance, I think, where you can actually select a probe that's in a cooler location. So you might be placing it in the hot probe, hot spot, but it'll be cooler than, let's say, the center of the chamber, because we're aware we want to control all of the areas with intolerance, but we're aware we can't place that center anywhere. It needs to be at a point close to that, the next worst case location potentially.
Yeah, and often what we see as well in those cases where it's impractical to place those sensors is also where it will feed back into the daily operation and also affect your alarm limits. Because if you are aware that you're measuring 0.1, 0.2 degrees below the actual hotspots, it's quite easy just to implement that into the daily monitoring by setting other alarm limits. It's not as such a critical factor. And I think also it also comes back to the basic nature of temperature mapping, which is always that it's a single point in time measurement, right? I mean, it will change the second after you take down your mapping equipment. The picture is going to be slightly different. Hopefully, it should sort of maintain within reasonable bounds, but that's why we do requalification, right? It does matter the second after.
And it's probably also worth mentioning that when you do that, the person who's performing the temperature mapping isn't the same as like a lab staff who are using it on a daily basis. So, you know, you come at it from the approach of we're mapping this unit, but it's a spot check run by somebody who's not the routine operator. It's no validation is going to be perfect. We've added sensors that wouldn't normally be there. You know, depending on the method of those sensors getting in the chamber, if it's something like thermocouples, they might be going in through the door seal, or if it's data loggers, they're taking up additional space. But there is a difference between mapping and real world. There always will be, but it's going to give us that additional information that we can sort of hang our hats on and say, you know, there is an issue at this location and we need to map it or monitor it because of that.
Then Niels has a comeback, and he disagrees with the use of remapping to identify defects on cooling systems. As an example, technical defects such as a fan failure should be identified through various controls in place, etc., like housekeeping, walks, trending, or change control and periodic equipment review.
Absolutely. He's right. I completely agree with him. Sorry. You're right. I mean, this is part of the periodic review process. There's some elements you just can't pick up on. A fan failure, for example, even during preventative maintenance, we're not inside the unit. We can't see if it's turning, and quite a lot of fans will turn off when you close the door, when you open the door. So it could be spinning in the wrong direction. These are not necessarily things that we can pick up. We can start to see some issues. So we're looking to see what we can see. We want to try and identify that in whatever method it might take. That might be temperature mapping, which will identify changes in hot and cold spots. It might show a location previously that wasn't a hot spot that is now out of tolerance, and that might impact the fan. So you can detect issues, but as he says, absolutely, if you put measures in place, you can start. You need as much preventative maintenance and operator knowledge as you can possibly get, really.
Absolutely. And where do you collect that? I know you do, but because housekeeping, it's probably several people doing this. From our experience, it could be many people doing the housekeeping, the daily housekeeping, and looking in the operators, like you call them, in the units. Because to my understanding, it's when we visit sites, it's sometimes there are binders over there in that archive, and then there are the basement with other binders, and then there's the third archive with the last set of binders. And we're talking about trends here, like that are manually kind of picked up on over time, like ice building up inside and stuff like that. But is there any good practice in making sure that you make these periodic reviews well and correct?
I think a lot of this comes down to well-founded training. I mean, if you have a good quality culture, I mean that's often what we see with our customers, that if there's a good quality culture in which the quality is understood and responsibility is shared, that there's a good understanding of why it's important. I think that's what makes the greatest difference. Also, in terms of course, the baseline is to have procedures in place and training in place. But I think often I see what I call operational excellence in terms of quality, where there's a really good quality culture, because both people feel engaged, but also because the impact that these things have on quality is understood and it is also adapted by operational staff.
Absolutely. It's got to be a mixture of everybody. It's got to be a mixture of sort of maintenance personnel. It's got to be a mixture of validation and temperature mapping people, as daily operators. It's easy for it to be missed. So if everybody understands the criticality of, say, ice buildup, or we can focus on that. But some things are just really difficult to identify. Ice buildup's an easy one because you can see it visually. But when you talk about a fan or a heating and cooling failure, no, it's not 100% that you're going to pick that up on monitoring systems, on alarm probes. You might see a slight trend change, maybe, but mapping, more likely to pick it up. It's a difficult one, but mapping really is telling us that during those 24 hours, it was within the temperature range and there wasn't any sort of obvious issues. Whereas the periodic review is going to say, the control, those locations within specification for the entirety, so, but it's not the only thing. We need people looking for certain things like ice,
Absolutely. Gentlemen, thank you so much. It's really been a pleasure to host you, and I must say, a very interesting debate. I'm so sorry that I might not have been able to put all the questions in place for the QA. But it's really been interesting. Thank you so much, Chris and Jakob. I must say that it's overwhelming with all the thanks in the audience chat. So thank you out there. It's really been a pleasure having you on board on this. Remember, we are here. We look forward to hosting other sessions like this together with Jan. Thank you also to you, Jan.
Thank you very much, Adam and Chris. Amazing talk. So great to be part of it. So make sure to join us on October 12th for our next incredible session.
Okay, thank you very much.
Yeah.
Right.
Have a good day.
See you all, guys. Cheers.